All right, let's dive right in. We're going to talk about a circuit that is, no joke, the unsung hero inside almost every piece of modern electronics you own. I'm talking about the phase-locked loop, or PLL for short. It's just an incredibly elegant solution to a massive engineering problem.
And what is that problem? Well, it all comes down to timing. I mean, think about it. How do you get billions, literally billions of components inside a processor to all march to the exact same beat? Or how does your radio receiver lock onto one specific station with pinpoint precision, ignoring all the others? The answer, you guessed it, is the phase-locked loop.
So here's our game plan. First, we'll cover the basics. What even is a phase-locked loop? Then we're going to peek inside the feedback loop to see how it works. After that, we'll talk about its limits, the capture and lock range. And finally, we'll look at some of the really cool real-world applications.
Okay, let's get into it. What exactly is a phase-locked loop? Well, if you boil it down to its absolute core, it's basically a machine built for one purpose, creating and maintaining perfect synchronization.
So what you're looking at here is a type of control system, and its one and only job, its whole mission in life, is to generate an output signal and then just constantly tweak it, constantly adjust it, until its phase and frequency are an exact match or locked to an input signal. It literally forces two different signals to march in perfect step.
Now, what this locking actually achieves can look a little different depending on where you use it. You know, in the digital world, a PLL is all about creating a super stable clock signal. This makes sure we get what's called bit synchronization, so data gets read at precisely the right moments. But in the analog world, it's more about generating carrier waves for phase synchronization, and that's absolutely crucial for things like radio communication.
All right, so now let's pop the hood and go inside this feedback loop to really understand the magic behind how this whole locking mechanism works.
Okay, this right here, this is the heart of the PLL. As you can see, it's all about the feedback loop. We feed in our reference signal, which we'll call it FN. It goes through three main stages: a phase detector, a low-pass filter, and a voltage-controlled oscillator. And that produces our output, Fout. But here's the kicker. That output signal, Fout, gets fed right back to the beginning. This is what allows the system to constantly compare its own output to the input and correct itself on the fly.
So where does it all begin? Right here, with the phase detector. Now, don't let the name intimidate you. This block is basically just a multiplier. It takes the original input signal and compares it with the output signal that's been fed back from the end of the loop. And what it spits out is an error signal, which we'll call E of t. This signal represents the difference, the mismatch, in phase and frequency between the two.
And for all you engineering students, this is where the math gets really cool. Because of some neat trigonometric identities, when you multiply two sine waves like this, the output isn't just one signal. You actually get two new frequency components. You get one at the sum of the original frequencies and another at their difference. And for what we're trying to do, we only care about that difference component. That's our golden ticket. It represents the error we need to fix.
So how do we get rid of that high-frequency junk we don't want? Well, that's where the low-pass filter comes in. Its job is to clean house. Think of it like a bouncer at a club. It blocks that high-frequency sum component and only lets the low-frequency difference component through. What you're left with is a clean DC voltage, EV, which is our pure, unadulterated error signal.
And this error voltage gets sent straight to our next component, the voltage-controlled oscillator, or VCO. Now, the VCO is the real workhorse of the PLL. This is the part that actually generates our final output frequency, Fout. And the beauty of it is right in the name, voltage controlled. The frequency it puts out changes directly based on the voltage we feed it. So a small error voltage means a small change, a big error voltage means a big change.
And boom, that's what creates the powerful feedback loop. You see how it all connects? The detector finds the error, the filter cleans it up, and the VCO acts on it. This whole compare, filter, adjust process happens over and over and over again, constantly nudging the output frequency, Fout, closer and closer to the input, Fin, until they are perfectly identical. At that magic moment, the phase difference becomes zero. That error voltage, EV, just flatlines. And that's when we say the loop is locked.
Okay, but here's the thing. A PLL isn't magic. It can't just lock onto any frequency you throw at it. It has very specific operational limits. And these limits are defined by two really important parameters, the capture range and the lock range. Let's start with the capture range. Think of this as the frequency window the input signal has to be inside for the PLL to even have a chance of locking on in the first place. If the input frequency is outside this range, The loop just can't grab onto it. It's like trying to cast a fishing line. But once you do get a lock, we start talking about the lock range, and that's the much wider window where the PLL can track any changes in the input signal without letting go.
And this diagram really illustrates the concept perfectly. Right in the middle, you've got the VCO's natural frequency, F0. That narrow band around it, that's the capture range. The input signal has to land somewhere in there for the PLL to get that initial lock. But see how much wider the other range is? Once it's locked, it can track the signal all the way from Fmin to Fmax. That's the lock range. This whole design is what makes the lock so incredibly strong and hard to break.
So that's all the theory. Pretty cool, right? Now let's get to the fun part and see where these little circuits are doing some serious heavy lifting out in the real world.
One of the absolute biggest uses is for jitter and noise reduction. I mean, you can feed a really messy, unstable clock signal. We're talking one with all sorts of phase variations, which we call jitter, and random noise. You can feed that garbage into a PLL, and what comes out the other side is a perfectly clean, stable, ideal clock signal. It's just an incredible signal conditioner.
Now, in the world of communications, PLLs are absolutely essential for something called clock recovery. See, when you get a stream of digital data, like from the internet, it's just a long string of ones and zeros. There's no separate clock signal that comes with it to tell you when to read each bit. So what does the PLL do? It looks at the incoming data itself, figures out the hidden timing pattern, and literally regenerates a brand new clock signal that's perfectly synced up. That's what lets your device read all that data without any errors.
And the list just keeps going. The versatility of these things is just amazing. They're at the very core of frequency synthesizers, which let us generate a massive range of super stable frequencies from just one single, cheap crystal oscillator. They're also fundamental to how we demodulate signals, like your car's FM radio, and they're used for generating precise tones in all kinds of devices. They're everywhere.
But maybe, just maybe, their most critical role of all is inside every single modern microprocessor. A diagram like this one shows a clock distribution network. What you have is a PLL taking one single master clock and creating this perfectly synchronized grid. Its job is to make sure that the clock signal reaches billions with a B of transistors across the entire chip at the exact same nanosecond. I'm not exaggerating when I say that modern computing would literally be impossible without this level of precision.
So look, if you take away just one thing from all of this, let it be this. The phase lock loop is the ultimate tool in an engineer's toolkit for achieving and maintaining perfect timing synchronization. Full stop.
And that kind of leads to a final thought to leave you with. As our electronics get smaller, faster, and way more complex, that fundamental challenge of keeping everything in sync only gets harder. It really makes you wonder, right? What will the next evolution of the PLL even look like to keep up with our crazy, relentless demand for more speed and more power?